Just to orient ourselves, we're going to look at the mental model overview to start. We've now looked through the mathematical formulation, and we've developed everything through the discrete finite element formulation for our application. The next piece is the elements, and then the basis and weight functions. And then, as we said, those all come together to create the entire finite element application, the finite element analysis for our application. So we've looked through the mathematical formulation. This is just a reminder. And really the next piece is the elements. So basically the idea is that you're going to take the domain and you're going to divide it. So if you remember the homework, the first homework, we talked about line segments. So we've essentially taken a line and we've divided it up into elements. Now the requirements for the elements are that they're continuous and non-overlapping. And this video will go through the mathematical foundations for why that's the case.
In this video, we're going to look at the elements. And in particular, we're going to look at the requirements that we need to meet when selecting elements. Let's start by considering the course mesh that we had as part of the homework problem. In that problem, we had a mesh where first element was at 0.0, 0.1, 0.25, 0.5, 0.75, 0.9, and 1.0. These nodes each had numbers associated with them. If you go back to look at the mesh, they were numbered sequentially. And your homework was to determine what the element lengths were. Okay, so each one of these was also associated with an element. So here we have element 1, element 2, 3, and so forth throughout the entire mesh for all 6 elements. Now, remember our integral, which we said was from x0 to xl of dwi, dx, dnj, dx, dx, tj, and that was equal to our right-hand side, which was the boundary terms. We can rewrite this integral as, the integral, well, what is our x0? X at 0 is also x of 1. So let's just do x of 0 to x7 to xl of our integral term. Put the dx in. So what we're going to do is we're going to say, okay, x0, that's the same as x1 now that we've numbered the actual individual points. And we can say we're going to do that to x2. There's our element. Plus, let's look at x2 to x3 plus x3 to x4 plus x4 to x5 plus x5 to x6 plus x6 to x7. So the sum of all of these integrals is the same as the sum from x equals 0 to x equals L. And furthermore, if you look at this, you can see that this distance from x1 to x2 is element 1. So that integral is over element 1. x2 to x3, this is over element 2. 3 to 4 is over element 3, and down the line 4, 5, and 6 down at the end here. So really, if you think about it, this is the integral over element 1, the integral over element 2, over element 3, over element 4, the integral over element 5, and finally the integral over element 6. So what do you notice about this? One, you notice that it's over the elements. That's the first thing. But what else do we notice? We note the following. 1, each integral is over an element. We called them line segments when we were talking about them in the homework. But the line segments in one dimension are elements. 2, notice that none of the integrals overlap. So none of the integrals overlap. And 3, each one of them is one after another. You include all, so you include all the integrals with no gaps. So number 2 here, this is our non-overlapping requirement. Number 3 is our contiguous requirement. And furthermore, from looking at that long expression, we can see that the integral from x equals 0 to xl, which we said was equal to the integral of, which was equal to all of the individual integrals, we can rewrite this as the sum of the integral dwi dx dnj dx dx tj, where we are summing over all of the elements, and the summation indices for the elements are the x local value at each endpoint. So x local 1 and x local 2, which will be the endpoints of each element.
Now that we've considered the elements, we understand what the requirements are, and we understand that we're splitting the integral up, and we're going to look at a sum of smaller sub-integrals over each of the elements. Now we need to consider the basis and weight functions, which will be the next video.